pleased to be introducing our first speaker of today, Tony Sudbery. He's a mathematician and Professor Emeritus at the University of York. He's worked in several areas of mathematics, philosophy, and theoretical physics, including quantum information theory. Currently, his main interest is the foundations of quantum mechanics. On that, Tony, please, the floor is yours.
Thank you, Charles. Well, I always start talks by apologizing for the talk, but I rarely have as much to apologize for as this time. So I'll skip the rest of the apologies. What I want to talk about is, I think, what everybody wants to talk about, and there's a number of people here. I believe that the world is a quantum system governed by pure quantum mechanics in Everett's terms. And I want to know what that means. But I haven't been satisfied by any of the answers that are normally given to that question. So I'm going to inflict on you my own answer and see if there's anyone left at the end of the talk. So in trying to work out what pure quantum mechanics means, I found myself having to look at a number of basic concepts. So in this talk, I'm going to talk about, oh no, why doesn't it work? We won't go to the next slide. That works. Well, I'm going to start by saying, what do I think is meant by the real world? And I find we have to talk about basic concepts like truth and reality, which will lead to something I'll call perspectives. I'll explain that when we come to it. And familiar topics or problems like superposition and probability. And I'll give you my own view of those. If there's time, I'd like to talk, well, if actually the main problem that has concerned me in thinking about my place in the world is, well, what does it mean to think about the future? So I'll have to talk about that. And I will present an answer in terms of logic. And if there's time, I'll talk about the past as well. That means memory. That's still not working. There. So what do I mean by the real world? What do us believers in Everett, us followers on the shoulders of Everett, mean by the real world? And I think we all agree that the whole world is described by a single universal state vector. I think universal wave function was Everett's phrase, which changes in time according to the Schrödinger equation with a given Hamiltonian, and that's all. In particular, there are no measurements in the basic postulates of the theory, in the basic ideas of the theory. There is no collapse upon measurement. Now, that means that all, something further, which I think all Everettians ought to agree, is that there are no special states in the basic foundations of the theory. There is no preferred basis. And I thought that these days everyone agreed on that, but I may have been wrong. But all the same, I think everybody should agree on it. That doesn't mean that all states are the same, of course. In this kinematics is the equivalent of Newton's equations of motion. And to get some physics, you have to say what the forces are in the equations of motion. You need to put in some dynamics. And it's dynamics that tells us what is the difference between different states. This doesn't mean that no preferred basis doesn't mean that all states are the same, that they describe different things. And we want to know, what do the different states mean? Well, there are 62 quantum fields in the standard model. Each of those gives rise to a Fock space, and each of those gives rise to an infinite number of bases, meaningful bases with different meanings in terms of many particle states. So all these states have different meanings. Given that, what has emerged over the last, 50 years, is that the idea of worlds is something that emerges from the basic equation. It's a matter of dynamics. I align myself with Lev Weidman, who thinks that what this means is that these different worlds are all partially real. Everett, at some point in his thesis, not in his paper, said that all these worlds are equally real, but I think we have to disagree with that. And there are a number of things in Weidman's, in Everett's thesis, which Wheeler made him change or omit in the published paper, and I'm on Wheeler's side. I think the changes he made were right. They were the right thing to do. You can go further than this. Some Everettians who call themselves fundamentalists think that you don't need these extra operators. You don't need anything. Everything is bound up in the Hamiltonian. And because of the unitary symmetry of the Hilbert space, that means in the spectrum of the Hamiltonian. And you can get everything out of that sequence of real numbers, which is the spectrum of the Hamiltonian. That's Sean Carroll's idea. He calls it the mad dog Everettians. Well, I wish him good luck with that. But I'm going to assume that there are definite operators whose eigenstates therefore give rise to states with different meanings. Now, I talked about the real world. I don't like the word real, and I'm going to have to talk about truth and reality. People often get concerned about whether the wave function psi is real. I think that's a category mistake. Psi is not a thing that may or may not exist. It's a description that may or may not be true. And I think it's much more helpful to talk about truth than to talk about reality. You may think, a lot of you will think, that I'm being very pedantic. After all, in ordinary language, real and true are used more or less interchangeably. But I think using the word real can lead us into wrong ways of thinking. I think it's much more helpful to think about things being true. So when people talk about whether your view of the wave function is ontic or epistemic, I think we should be using the words alethic for truth or doxastic for opinion or belief. Do you think that'll catch on? No, nor do I. However, concentrating on truth is not simply unproblematic. Oh, it worked. Let's go back to Schrödinger's cat. The Everettian description of the world in which Schrödinger is doing, or Schrödinger's diabolical experimenter is doing his experiment, is that the state of the world, which I'm reducing to a cat and an observer, is given by this expression. There is a term in the state vector in which the cat is still alive and the observer is happy. And there are an infinite number of terms in which the cat has died at a particular time. The observer sees that and the observer says so. So in these states, we have a number of propositions, of statements, as well as a statement that this is the whole truth about the world. Which of those statements is true? If you look at one of these statements that is made by an observer in the system, well, that is a physical state of affairs. That's a physical system, but it's also a statement. It's a statement that is believed by a human brain that has observed the facts that correspond to that statement, and those facts are real things, are in the world. From a purely human, from a scientific point of view, that statement could not be more true. And the same is true of all of these. But they can't all be true because they contradict each other. So how are we going to resolve that? Well, I rely on the philosopher Thomas Nagel, who talked about the different perspectives in which we say different things. You can regard this as a way of having your cake and eating it, if you like, but I think it's helpful. So let's suppose that the universe contains a particular sentient system, like me or you, or maybe like the whole human race, so that we can divide the Hilbert space of the whole universe into a tensor product of that sentient system and the rest of the universe. Then the universal state vector can be decomposed with respect to an eigenbasis of the operators which define the experiences of this sentient system. For simplicity, I'm supposing that those states are non-degenerate. Of course, that's a wild simplification, but it makes it simpler to present things. In that case, there are different perspectives. You can talk about the external perspective, what Nagel called the view from nowhere, the view from outside. We are looking at the universe, God's eye view, in which the whole truth is this state vector, this universal state vector, which of course is entangled between the sentient system and the rest of the universe. But you could also look at the internal perspective, the view that is made by any one of, well, it's made by the internal system, and that depends on which experience the system is having. So this is, it's not absolute, it's relative. Relative to which particular system I picked out, which sentient system, relevant to a particular experience of that system, and relative to a time, t, that sentient system, that observer, that agent, is organism, is allowed to say, I know that only this experience is real because I'm having it. I know it's real. And therefore I can deduce that the state that goes with it in the state of the universe, which is what I see, that is also true. I've color-coded these statements, as you'll see. The external perspective is in red. The internal perspective from relative to each of these things is in blue. However, I do have access, I think, partially, to some red statements, because I've worked out the state of the whole system, of the whole universe, or at least part of it, starting from my experience at a particular time, and what the experiment that I've set up and what I know about the dynamics of quantum theory. I know that there will be a superposition in which I am split into a number of different experiences. So I know that that superposition of my different experiences is true from the external point of view, not from the internal point of view, because I can't have all these experiences at once. The other experiences which I don't have are ones that from my perspective haven't happened, but they might have happened. Well, what's going on here, of course, is there's entanglement, which is caused by superposition. So how do we look at superposition? In which case I introduce my favorite title for a slide, which is that, or perhaps I ought to punctuate it. If I think that a state vector is a proposition, then the superposition of state vectors is a logical connective. The plus is a logical connective. The only logical connectives we have, or we used to, are and or. So which is this? Does it mean and? Well, in many world theory, people do take it to mean and. Does it mean or? In the lab, we do take it to mean or. It gives you a range of different possibilities for the results of an experiment. Or is it somehow something which can be and in one perspective and or perhaps or in another perspective? And I do think of superposition of state vectors as being superposition of vectors, like the vectors that we're used to. So a ship which is traveling northeast, its velocity vector is pointing northeast. But certainly that's what you would get if you say that the ship is both traveling north and traveling east. Of course, the same is true if it's traveling northeast. I should say, that's the state about the travel of the ship. It doesn't mean that there are two ships. There is not a ship traveling north and another ship traveling east, which is a way of thinking, a way of talking that I think the many worlds view tends to make you think about. People talk about all of their descendants in the future of quantum theory, as if these were different people. Well, similarly, a ship traveling north-northeast is also traveling north and traveling east. But of course, it's not the same. They're not traveling equally. A ship traveling only 1 minute of arc east of north, well, according to branch counting, that's also traveling east, but it's hardly traveling east at all. So in all these situations, traveling north and traveling east obviously have different values. What I would like to translate that into is to saying that the statements, the ship is traveling north and the ship is traveling east, have different truth values. Well, that's just a suggestion. I certainly haven't justified that yet. But what it suggests is that if you look at a state vector, if that is the whole state of the world, then it's true. It has truth value 1. But any other state is not simply false. Ones which have an overlap with psi have a partial truth value, a truth value given by the overlap between the two states, which is between 0 and 1, these being normalized states. Well, what we would usually think of that as is a probability. So I have to look at probability. Some people say there are lots of theories of probability. I think there are lots of perfectly valid concepts, all of which have the same name as probability. It's a very ambiguous word, and we have to sort out what we mean. Originally in, was it Pascal or Dominique Laplace? In the original investigations of equally probable possibilities, you simply count it up. It was a frequency. And that tends to be the working physicist's view of probability. What we're looking at is the possible results of a measurement, and we simply count up the possible results. But it can also be interpreted by some commentators on quantum mechanics as a measure of belief. And some important probabilists, Stefanetti and Jaynes, who was a physicist and a probabilist, but how much actually who did believe in hidden variables, think that this is just, probability is simply what you believe, nothing to do with the truth. And cubists tend to take the same view. And that is measured by looking at the betting odds that you're prepared to place a bet on. According to decision theory, a probability is simply a guide to action that will give you the best outcome. And that's also a component in cubism. It can also be regarded as a measure of how much you care about different possibilities. That's Hilary Greaves's suggestion. According to Keynes, it's a logical concept, which gives you a relation between one proposition which is entailed by a number of others. It gives you the degree to which that entailment is certain. According to Popper, a probability is a propensity, which just seems to me to be using a different word. But what I think he means by that, I think that's the same as what philosophers call objective chance, which I must admit to me is the most attractive form of probability. So, and notice that some of these, not all of them, involve the future. They only refer to what's going to happen in the future. They need the idea of the future in order to make sense. So which one should I choose? Well, what's my situation? I'm very old, I'm very retired, I'm very lazy. I have a comfortable time sitting in my garden in an armchair, reading the newspapers and watching my grandchildren grow up. I don't do any experiments. I never did, actually. But I'm retired, I'm no longer professional. I don't make any measurements. What Copenhagen says about probability means nothing to me. I don't even take any action. I don't make any decisions. I don't have to anymore, thank God. So decision theory is completely irrelevant to me. I don't gamble, never have done, don't place a bet. So you can't use that to measure my degree of belief. And anyway, I don't have beliefs. I don't care either about what's going to happen. I'm just interested in it. I know that there's nothing that's definite that's going to happen, but I'm interested in what is likely to happen. It's got nothing to do with anyone doing an experiment or making a measurement. I want to know all the time. And I expect physics to tell me what is likely to happen. And I think that would be an objective statement about the world. What does it mean? What does probability mean for a purely passive observer like me? Well, I have a suggestion. I'm thinking of Schrödinger watching his cat. He's going to open the box in an hour's time. Will the cat be alive or dead? The cat will be alive is not true, because it might not be. The cat will be dead is not true either. But it is true that the cat will be either alive or dead. And actually, this discussion goes back to Aristotle, who discussed the meaning of phrases, of sentences in the future tense, describing things which are not determined. Aristotle didn't have a Newtonian physics in his background. He thought that there were things which are not determined. In that case, he gave the example of the Persian forces were massing outside Athens, I think it's Persian, and he wanted to know whether there was going to be an engagement in the sea. Will there be a sea battle tomorrow? Well, we don't know. There might be. There might be a standoff. There might not be. So the statement that there will be a sea battle, there should be sea battle. That statement, corrected statement, there would be a sea battle. There certainly will be a sea battle. That sea battle tomorrow. That statement is neither true nor false. He was talking about truth values and talking about logic, and pointing out that there are statements in which bivalence does not apply. And a similar thing was applied to quantum mechanics by Greta Heermann. Now, that's not quite true. She said in quantum mechanics, truth is split. But what she was referring to actually is more like what I was talking about earlier with the truth in different perspectives, not different truth values. But that idea was taken up by Łukasiewicz, the logician who introduced the modern idea of many-valued logic. And his motivation for doing that was precisely in order to talk about future contingents which are not determined by the present. He thought they should obey a many-valued logic, but many in his case meant just three. He just had one value of truth which was not true or false, and that was undetermined. I'm going to suggest, in common with some other people, that we should identify the truth value of a future tense proposition with its probability. Now, Simon Saunders might not relish being cited in this context, but I think this idea can be found in some of his earlier papers, where he was talking about the indefiniteness of the future. And Jaroslav Puchacz has also talked about many-valued logic as a framework for quantum mechanics, so his framework's a bit different from mine. That leads us to a logic in which we need to talk about statements that have a tense, statements that are in the future tense, possibly in the past tense, but I'm going to concentrate on the future. Quantum logic has propositions which are represented by closed subspaces of Hilbert space, which can be replaced by the orthogonal projections onto those subspaces. So I'm going to represent propositions by projectors, pi. To talk about future and past statements, we need to also introduce the same propositions, but with a future tense applied to them. And also some in the past, but that's the same as having this same opera F, but with a negative T. The logic, that is the connectives, but the lattice of propositions at a given time is given as usual, but as was given by Birkhoff and von Neumann in terms of the intersection and the linear sum of subspaces. When you're comparing statements from different times, then if we take basic projectors at different times and say they're all true, give the conjunction of them, what we've got is a history. What's the truth value of a history? Well, if you think of these projectors as representing measurements at these different times, then the ordinary Copenhagen interpretation of quantum mechanics, the one you find in textbooks, tell you that there is a probability for each of these measurements at each time, and after each measurement, the system is projected onto the result of the measurement. And that gives you a probability for a sequence of measurements, which is given by this familiar formula in terms of a history operator, or chain operator, composed from the projectors at each individual time, moved forward from the time zero by the Hamiltonian. But that depends on, it results from the assumption of the collapse postulate at each of these times. And I think that that's an unfortunate result of an ambiguity in the meaning of a projection. It can mean a proposition. It can also mean an action on the state vector. Given that, you can complete the logic with truth values for disjunctions, for or, by a formula which is familiar from probability theory. That only makes sense if you introduce the assumption, which I haven't done up to now, that all of these histories obey a consistency requirement, not the whole strength of that requirement, but part of it, which looks, this all looks ad hoc to me. Why should I believe this? Why are there all these projections? I don't believe in the collapse postulate. Why do we have to have this consistency requirement? There's an alternative. Oh, damn. Oh, I can't go to my next slide. That does it. There's an alternative possibility, not alternative formula for the probability of a history, which I've taken from a formula that Bell wrote down, a process that Bell wrote down in the context of Bowman mechanics, which is not what's going on here, but the formula is the same. So the question is, I'm only interested in projections which represent definite experiences. And then there are subspaces of the whole universe which represent me having a particular experience. So I apply the projection to my factor of the universal Hilbert space and leave the rest of it alone. In other words, I simply pick out the term in that expansion I showed you earlier, in which I have a particular experience. If I'm having that experience, what is the probability of a set of future experiences? Well, this is purely from my perspective. This is an internal statement. I should have said earlier that I think because of the determinism of the Everettian view of the universal state vector, probability simply is not appropriate to the external view. Everything is determined, probability is not relevant. Probability only comes in if you're looking from the internal experience of a particular sentient system. So from that perspective, there is always a definite experience going on. I always have a definite experience. That's the way I define experiences. So the universe is always in one of these subspaces corresponding to a definite experience. Bell says if it's in a particular subspace, then it might jump into another subspace at a later time. It might stay in the same subspace. The probability that it will jump is given by this transition probability in time delta t. That's right. Which is given by this expression. You look at the matrix elements of the Hamiltonian between the components of the universal state vector in those subspaces at that time, and see if that is positive. If it is, you count it. If it's not, you say that transition simply didn't happen. It only happens when this is positive. This has the value that it reproduces the Born rule. Assuming that you've got states distributed according to the Born rule at time t equals 0, this will always be true if the system is following this process. Something I wanted to say that I've forgotten. Okay, so it's not the only formula for transition probability which would give rise to that result. There's a whole sequence of them. Labeled by a parameter between 0 or 1. But this is the one which gives you sensible results in particular situations, like exponential decay, for example. So I think that's a good reason for choosing this one. You might think it's ad hoc. So you see that the change in my experience is driven by the universal state vector, which includes all the experiences I didn't have, and by the universal Hamiltonian. Well, I've been talking, so I've had half an hour. Should I jump to the conclusion, Charles, or shall I have another 5 minutes?
Yes, you can take your 5 minutes, Tony.
Since we wasted a quarter of an hour at the beginning, perhaps I'll
yeah, well, we are adaptable.
Okay, well, classically, I don't mean classical physics. I'm going back to classical times. So Aristotle would have thought that any statements about the past and the present are either true or false. It's only the future which is indefinite. And that would not be true in the quantum mechanics that I presented so far of a particular experiencer. He's not sure what his past is, unless he's got a memory, which tells him or her. So this could also be true if the organism splits into the experiences I've been talking about so far and a memory which gives you a record of past experiences. So I replace the particular experience states by states in which there is a memory going far back into the past and with a state telling you which of these experiences happened at each of those times in the past, but tells you nothing about the future. There's a further state which is just unknown in the future. And this changes as the experiences changes, so that the state at the particular time, the state in the memory corresponds to what you are actually experiencing at this time. If I tried to do that with continuous time, it wouldn't work because of the watched pot effect. So we need a finite time resolution in the memory in order for this to work. But if given that, and if we now use these experience states to work out the probability according to that Bell process, we find we do come back to what Copenhagen would have said. These existence of the memory forces the appearance of a collapse in the state at each of those times because of entanglement. So essentially collapse is equivalent, it's driven by entanglement, which means it can't be applied to the whole universe. So the formula in consistent history theory, applied to cosmology, is free floating. It's not well founded, I believe. So, conclusion. There are different logics. There's the logic that applies to God, looking at the whole universe. The propositions in this logic are the ones given by quantum logic, by Birkhoff and von Neumann. They're closed subspaces of the universal Hilbert space, represented by projectors onto those subspaces. So that's a non-distributive lattice, as everyone knows. We extend this to temporal propositions, which are given by histories. And now, from the external point of view, what is the truth value of a history? Well, this is not the same situation as was envisaged by the consistent history theory people, because we're working in Everettian theory where there is a universal state vector with definite values at each time. And the truth of any projector is given by projecting that universal state vector and seeing to how much that corresponds with the actual fact, that is the universal state vector itself. In other words, we look at a matrix element of that projection operator at that particular time and just multiply them together. That's a different probability formula, which I haven't explored much, actually. If we look at just one time, so we take a history to be a history consisting of a projector at one time, then we can say something that might sound more familiar. At a particular time, the value of the universal state vector is the truth. It has truth value 1. Any other state vector, which is not the truth, but it's not completely not the truth. Doesn't have truth value 0, but it has a truth value given by its overlap with the actual state vector. Or you could say, I think Lev Weibman would say this, at time t, this other world, phi, has a degree of reality, which is given by its overlap with the universal state vector. And so, of course, in the situation which Zay and Jurek and David Wallace have explored, where decoherence gives you a superposition of worlds, then we can look at those particular worlds. There's a lot of them being superposed, but they're not all completely real. They have a lower degree of reality. Or we can look at the internal logic, where we're only concerned by propositions about a particular experience, and therefore we're looking at a Boolean algebra. There's no question of not being distributive. And then, in the perspective of a particular subsystem, a particular experience, and a particular time, that experience is true. I know it is. I can feel it. Therefore, I can possibly work out. Now, this, of course, is not going to be as precise as this makes it look. But from this, I can say something about the rest of the universe because my experience refers to the rest of the universe. I'm seeing things. And that is part of this psi n dashed. But then I can work out the future, and I don't have exact knowledge. All I can say is that there is a truth value for all of these different experiences. And to work out this probability, I need to know the universal Hamiltonian and the universal state vector. And what does that mean to me? What's the truth for me is the experience I'm having. So what's this universal state vector? It is not a state vector. It's not a description of a state of the world. The state of the world is given by what I see. This is an influence. It's something which changes what I see. It's like a force on my experience. Or to put it as Vlatko-Vedval has put it, unobserved results which are still there in the universal state vector can affect the results of new future measurements. And with those words of wisdom, I'll finish.
Thank you very much, Tony, for the beautiful talk. If anyone wants to join me in a round of applause. We have, in an attempt to make it up, let's take one short question and then we'll stop the recording and we'll be able to make it back on time. So if of course, someone has a short question. I see a hand raised by David Wallace. David, would you like to ask your question?
Thank you, yes. I wanted to ask about something specific about your example with the ship that there isn't both a ship going north and a ship going east. You want to say there's a ship going northeast. I'm kind of worried how that's going to play out in quantum theory in contexts where you haven't got like a definite set of classical objects which you could say have indefinite quantum states, but where what the objects are is part of the superposition. I mean, we happily talk about a cat that's in a superposition of alive and dead, but the atoms of a cat can perfectly well be assembled into a bunch of small mice or something. So it's only in special cases we could even say there's a cat which has an indefinite state. Mostly we could say, the best we could say would be something like there's a bunch of atoms such that it's indefinite whether there's a cat or not for those atoms. And even then, once you go to QFT, the atoms are not eternal things either. The best you're going to be able to say, I've got some region of space such that it's indeterminate whether it contains a proton or not. I mean, so I wonder in practice when you whether there's really as large a distinction as you were drawing at that point in the talk between the two situations.
Between two which situations? The situation. I mean,
between the idea that I've got something which has an indefinite property, and the fact that I've got.
Okay. Well, now you understand if you don't follow me in this. There is something which you can say you don't know whether it has a definite property, and that is the whole universe. You don't know whether the indefinite property is whether those atoms are assembled into a cat or into a nest of mice. So what we get with the superposition is something which I'm going to say is sui generis. It's something peculiar to quantum mechanics, which I'm prepared to accept. A lot of people wouldn't be. We don't really know what it means. We just accept that that is the mathematical description.
Yeah, so I can live with that, but I think once one acknowledges it's just that the only thing you can actually apply this to is the whole universe.
Absolutely,
the distinctiveness drops away. I mean, one can't talk about ships being indefinite in what they're doing, or cats being indefinite, or anything other than the whole universe is such that it's indefinite.
That's absolutely right. I totally agree with that.
Thanks.
All right, so that will be a perfect place to stop the recording.